All right, so we're back to talk about the electric field due to planes of charge. And I've got drawn on the screen two different kinds of planes. I have an insulating plane and I have a conducting plane. And then I also have side views drawn for those, because what we want to talk about is where the charge is actually going to be located if it's an insulator versus if it's a conductor, because it's kind of a big deal. So our goal is really to find the electric field some distance x above a plane. Above a plane of charge. Okay, and this is one of those situations where x is much, much less than L. So how high we are above the plane is much, much smaller than the sides of the plane. And what that's going to do is it's kind of like, again, the analogy we keep making with the Earth. If you're looking at the Earth from far away, its gravitational field changes in direction. But if you look at the Earth from our perspective, the gravitational field is constant in direction and in magnitude. We're looking at this situation so that we can use the approximation, this x much, much less than L, so that we can say the electric field is basically constant, uniform, in strength and in magnitude, in magnitude and in direction above this plane of charge, whichever kind of plane of charge we've got. Okay, so with that in mind, let's talk about how the charge is going to be distributed on our either conductor versus our insulator, and that'll help us take a look at what the electric field is going to look like there. So on the insulator, for an insulated material, you can have charge on the top, you can have charge on the bottom, you can have charge distributed through it. We're going to act like our charge is just spread. Oops, I have it on eraser. That's no good. We're going to act like our charge is spread straight through the middle of this. Okay, so it's just a single line of charge spread through this insulating material. So there's just charge everywhere on this plane. On the conductor, even though I didn't give it a thickness, the conductor has like a top surface and a bottom surface. And we know that charge only resides on the surfaces of a conductor. If you add charge to it, it doesn't stay in the middle, it spreads itself on the outsides. So this would be drawn slightly differently. I draw charges on the top portion and on the bottom portion of this thing. And then we have to talk about, well, how do the amounts of charge compare? Like, how does this amount of charge through the insulator compare to this amount of charge that I've got drawn on the inductor, or on the conductor? So we'll pause that for a second and then I'll start talking about it. If you're coming back to the video now, I'm coming back to it after having a long pause where a class finished, people left. I wrote some things out, did some other work, and came back to it. So if the video suddenly just has a disconnected nature to it, it's because there was about a 20-second pause here and a half-hour pause in between where we just were in the video and where we are now. But our goal was to be able to calculate the electric field due to a plane of charge and look at it whether that's a conductor or an insulator. Okay. Your textbook makes a big deal out of the difference between the electric field and a conductor versus an insulator, and showing under what circumstances these two things are the same and what ways we would yield a different result. And it's all about how we describe charge density. Then in the end, what we're going to show is that the electric field due to this plane of charge versus this plane of charge is going to be exactly the same thing. But it's all about how you're using Gauss's law to figure this out. So let's start off with the insulating plane of charge. What we need to do is draw a Gaussian surface for this. So my Gaussian surface is going to be just anything with a flat top and bottom. So I'm going to draw like a smaller box. Some people would like a right cylinder that extends above and below this plane. And so I'll draw it on this picture, but I'll also draw it on here. And it's got a height x above this surface. So here's my Gaussian surface. It's going to go above and below this plane from the side view. And again, the height of this thing is x. Okay. Well then, Gauss's law says, take a look at the net flux through your 3D Gaussian surface. And that's going to equal the product of E dot dA on all those sides, and that equals the charge enclosed divided by E0. Okay, well, on our surface we have 6 different sides to this Gaussian surface, and really a bunch of different regions and different things going on in each one. So I'm going to break our integral up into 3 different chunks. E dot dA for the top of our Gaussian surface, E dot dA for the sides, and E dot dA for the bottom. And then talk about what's going on with the dot product and what's going on with the integral for each of those different chunks. Okay, on the dot product nature of this, the electric field due to this plane of charge, we said is basically going to be a uniform field. So it's going to point straight up because of what we were saying about the Earth's gravitational field versus this. It's going to point straight up like that. So it's kind of like when we're close to the Earth's surface, we treat gravity as though it's a constant field. And it's also going to point straight away from this. It's going to point down through our Gaussian surface. So uniform in direction, uniform in strength. All right, well, if that's our electric field, the dot product of that electric field with the area vectors on the 4 sides of this thing, that's going to be 0 because the area vector is completely perpendicular. So really we're only looking at the flux through the top and the bottom. That's where our net flux is going to be. I think I said net flux. So that E dot dA, well then my electric field vector and my area vectors are perfectly parallel to each other. So this E dot dA for the top just becomes E times A for the top. E is constant at all points across that, so I can pull it out of the integral, and then dA just integrates to the area of the top. Same exact rules for the bottom. So this is E times A for the bottom. And that equals my charge enclosed divided by E0. Okay, now since I'm kind of old school, the area that I'm talking about, I do not draw my Gaussian surface to extend all the way out to the edges because I want to make sure that we can make the assumption that there's no fringing in my field, that my field really is uniform. So I'm going to calculate the portion of the charge that's actually enclosed. So I'm going to say charge enclosed over area enclosed is equal to total charge over total surface area of my Gaussian surface. Okay, of my total charge, the total area that actually has charge on it of my charge plane. And this, for the conductor, all my charge Q is just in a single line through there is what I'm saying. So as I calculate that charge enclosed is just Q times A times the area enclosed. And my area enclosed portion is just, let's change this to green. My area enclosed portion is really just this area here, just like that 2D top, it's like a single plane of charge that has, or a single plane of area that has charge on it. So that's really just a 2D surface. So that area that's enclosed, this, is really the same as the area across the top or the bottom of my Gaussian surface. I'm not worried about this having a thickness. In the case of the insulator, it's not like there's an above or a top surface and a bottom surface to this. It's not like this has any real thickness. So then I can say that E times area for the top plus E times area for the bottom is equal to the charge enclosed, which is that total charge Q, divided by the total area of my plane times the area enclosed. This area and this area and this area are really all the same size areas. Okay, so these areas cancel out. It's really just the portion of this plane that has charge on it, that portion. So then I get that 2 times E is equal to all the charge over the area over E0. I left out an E0 here. And so my electric field just comes out to be Q over 2 times area times E0. And if you're a person who likes to write this charge per area in the notation we started to learn today, charge per area is often used, or is often described by the symbol sigma, which I call tired 6 over 2E0. Okay, that's what we're going to get. And this was for the insulator. Okay, for the conductor, I'm going to get something really similar, but I'm actually going to do that in a separate video.